Welcome to another Explainer. Today, we're diving into topic 14, bearing capacity. It's kind of the ultimate engineering mystery. Think about it for a second. Every towering skyscraper, every massive bridge, every home rests on what is essentially just dirt. But how do engineers actually know the ground won't simply give way? Today, we're stepping into the shoes of geotechnical detectives to uncover the hidden science of how we manage to build safely on the Earth.
So here's our roadmap for this Explainer. We're going to hit the foundation of foundations, decode some terminology, look at two main ways things fail, dig into the math and models, and finally, talk about testing the real world.
All right, let's kick things off with part one, the foundation of foundations. This is where we ground the mystery, right? At the critical zone where concrete and steel finally meet the earth.
So, it's a simple question, but really pose this to yourself. Why don't buildings just sink? I mean, you've got thousands, sometimes millions of tons of material pushing down. There are massive, invisible forces at play right beneath our feet, and the soil has to push back with the exact same amount of force. If it doesn't, well, gravity wins, and the whole thing goes down. And that brings us to the star of the show, bearing capacity. Basically, it's the load-carrying capacity of the foundation soil or rock. This totally reframes how we should think about the ground. For engineers, soil isn't just dirt you scrape out of the way. It's a legit structural material. Just like a steel beam, it has a specific capacity to carry weight. Figuring out that exact capacity is absolutely crucial.
Moving on to Section 2. Let's decode the terminology and peel back the layers of this geotechnical onion to understand the vocabulary engineers use.
Okay, we've got to start with the absolute limit, the ultimate bearing capacity. This is the maximum pressure a foundation can take before the soil physically breaks apart. Engineers call this shear failure. If a building actually hits this ultimate number, you're not just looking at a cracked wall. You're looking at a catastrophic collapse, where the ground literally shears and gives way underneath.
But, engineers have to be way more precise than that. Think about it. The ground at a certain depth is already holding up the weight of all the dirt sitting on top of it. So, we distinguish between gross and net capacity. Gross is the whole shebang. It includes the pressure from holding up the dirt itself. Net capacity strips away that original overburden pressure. It isolates exactly how much new weight, like the actual building, the soil can handle.
Now, here's the kicker about that ultimate limit. We never, ever want to get anywhere near it. No way. In geotechnical engineering, the standard factor of safety is usually 3. It can range from 2 to 5 depending on the soil and structure, but 3 is the go-to. What this means is an engineer calculates the absolute max load the ground can take and then literally divides it by 3. That massive safety buffer is the invisible shield keeping you safe in whatever room you're sitting in right now.
So, the big takeaway here is that we never design to the absolute limit. By taking that net ultimate bearing capacity, dividing it by our huge factor of safety, and then adding back the surcharge pressure of the soil depth, they get the safe bearing capacity. That's the golden number. It's the maximum intensity of loading that can be put on the soil without risking that catastrophic shear failure.
All right, Section 3. 2 ways to fail. The twin threats. Because avoiding a sudden collapse isn't the only mystery we have to solve here.
Turns out, the ground can fail a structure in 2 completely different ways. First up is the shear strength criterion. This is that sudden, catastrophic rupture we were just talking about, basically an underground landslide right beneath the footing. The second threat, the settlement criterion. Now this one isn't sudden. It's a slow, crushing sponge effect where the soil elastically or plastically compresses under the weight. It causes a structure to sink unevenly over months or even years, slowly tearing the building apart.
Since these twin threats are completely different physical mechanisms, engineers actually have to investigate both of them independently. They crunch the numbers for the maximum pressure to avoid shear, and then the maximum pressure to avoid settlement. The final design number, which is called the allowable bearing pressure, is strictly whichever value is smaller. The bottleneck always dictates the design, which is how we can be absolutely certain the building is going to stand tall.
That brings us to Section 4, Math and Models. Let's look at the forensic tools used to actually predict these failures before a single shovel hits the dirt.
Our forensic toolkit has evolved a ton over the last century. Believe it or not, we went from basically crossing our fingers and guessing, to applying Schleicher's theory of elasticity, to classical earth pressure theories from pioneers like Rankine. Today, modern engineering leans heavily on the theory of plasticity, championed by legends like Carl Terzaghi. And these aren't just equations. They are intense mathematical models predicting how millions of dirt particles will interact under immense pressure.
Terzaghi's bearing capacity equation is frankly legendary, but rather than bogging down in all the complex algebra, just look at the logic in his quote here. He breaks soil strength down into 3 distinct fighters battling against collapse. First, the cohesion of the soil, how sticky the dirt is. Second, the weight of the soil, how heavy and dense the ground itself is, which naturally resists being pushed aside. And third, the depth of the foundation. Basically, the deeper you bury the footing, the harder it is for that soil to escape upwards.
Okay, Section 5, testing the real world. Because let's face it, math on a whiteboard only gets us so far. The Earth is messy.
So here is the ultimate challenge. How do we actually calculate this out in the field without just guessing? We can't always just take a tiny, pristine sample back to the lab. We need to know exactly how the whole site behaves right there in place on a chaotic construction site.
We do it by literally interrogating the ground with some pretty intense physical tests. Take the standard penetration test, or SPT. You're rhythmically slamming a heavy steel tube deep into the earth and counting how many blows it takes to drive it in. Then there are plate load tests, where engineers load massive weights onto a steel plate right on the site to see exactly when and how the soil starts sinking. And for sticky cohesive clays, they pull undisturbed samples and literally crush them in unconfined compression tests.
Now, what's super fascinating about Terzaghi and Peck's work is how it bridges the gap between raw, dirty field data and those pristine mathematical equations. It links the end value, which is literally just the number of hammer blows it took to penetrate the soil, directly to those complex bearing capacity factors we mentioned earlier. We're taking something as brute force as pounding a tube into the dirt and using that correlation to unlock the mathematical secrets of the soil.
And when it comes to that slow sinking settlement threat, the math brilliantly illustrates the final verdict. By looking at established data, an engineer can take the width of their planned footing, match it up with their specific hammer blow count, and instantly determine the exact allowable bearing pressure. It tells them precisely how much load that foundation can take before the building settles more than an inch, or 25 millimeters.
But the real genius here is the extrapolation. I mean, we're doing a plate load test on a piece of steel roughly the size of a pizza box, but the math has to perfectly scale up to a prototype foundation supporting thousands of tons of concrete and steel. Engineers use perimeter area ratios to ensure that whatever happens to that small model in the dirt perfectly predicts the behavior of the massive structure being built.
It truly is a remarkable hidden science. So the next time you walk into a towering skyscraper, or honestly even just stand in your own kitchen, I hope this changes how you look at the floor. Beneath you isn't just dirt. There's a whole web of invisible math, rigorous field testing, and a silent factor of safety working around the clock to keep the Earth exactly where it belongs. Thanks for joining me on this explainer, and keep questioning the world beneath your feet.